Hello, everyone. I'm going to start by talking about my brother. My brother is 7 years older than me. He's also a programmer. And although I had a great role model in terms of software development, understanding that it was a real job, and I was a geek and I was into math and I programmed BASIC at a fairly young age, I never actually thought I was going to go into the computer field. I really didn't. I just didn't expect it. To the point that when my small town got its first ISP and I wanted to get on this thing called the internet, I actually decided to pay my brother to build me my first computer because I didn't want to mess with that. I just thought, that's his problem, that's his thing. And he built me one, and it looked like this. I gave him $500 of money that I'd earned working as a waitress at Applebee's, and it had 16 megs of RAM and a 2 gig hard drive, and Pentium was new, and so that was a cool thing, and then a 28 mode, of course. And I thought it was awesome. I thought it was the greatest thing in the whole wide world, and I was really happy that my brother could do this for me. And by having this, I've now pretty much dated myself. You all know how old I am. But it was kind of necessary for the talk in order to kind of illustrate that over time, and this is a graph of the sizes of hard drives over time, starting from 1980 all the way through 2010, that we went from about here when I graduated high school to we're here now. And we've had some rapid growth in that front. And so now, of course, RAM is measured in gigabytes and storage is measured in terabytes. And since we're in Kansas City, I do have to rub it in a little bit. Data transfer is in gigabits, and I actually live in Overland Park, so I am not blessed yet. But we did find out that they are finally coming to Overland Park in 2015, so I'm excited. Yes, yes. So we've gotten a little spoiled. Things have advanced to the point where we have really high expectations of the machines that we're running on. And sometimes from a software development standpoint, we are spoiled in terms of the decisions and the trade-offs we make in optimizing for those resources. But we're not spoiled everywhere. Julia talked about the Pebble this morning. That has about 32 megs of space. If you have a Garmin Nuvi, and it's a nicer one, you have about 8 gigs of space. And if you're ever thinking of buying a Tesla Model S, just so you know, the entertainment system, the in-dash entertainment system, has about 16 gigs of space. So it's not the same when we talk about these more embedded devices. And making things worse is that what we want from our software is keeping pace with our capabilities in software. Whenever we make an advancement in terms of the amount of resources we have, we want to do more with it as well. So if you want a map of all of North America on a device so that you don't have to connect to the internet in order to see where you are or get directions, we're talking 2.5 gigs to store that. If you want a whole bunch of songs, they're about 1.5 megs a piece, and if you have an extensive collection, that can add up. And if you're like me and you want your kid to be able to watch movies on airplane flights or on long trips on the iPad, then we're talking about 4 gigs of space for an HD quality movie. And that's just talking about drive space, of course. That's just one of the resources that we have at our disposal as software engineers. So I think more and more what we're going to see is this kind of race going on, where we have this need for very data-driven applications, but we want them to be portable, we want them to be mobile, so it's a very resource-limited world in which they have to exist. But the good news is that everyone is getting to this place, right? We're not alone. Everyone's talking about how do we get these mobile applications, how do we do things. And as software engineers, when we're faced with a common problem, someone steps up and comes up with something to help with this. So maybe it's a data format that's more efficient than previous formats we've worked with. Maybe it's a new compression algorithm that helps us store the data more efficiently. And they exist. We have tons of options. We have Avro, we have Protobuf, we have just general compression like Zip. We have BSON, we have Smile, which is faster XMLs, efficient storage for JSON, and then, of course, Apache Thrift. Tons of options, and this is obviously not an all-inclusive list. There's many more. But when we're evaluating options, we have to have a means to compare them, of course. And the nice thing about compression theory is that it's really dead simple. You take the size of how it started out to be, and you divide by the size of where it ended up, and you get this ratio, and that kind of tells you what it did, and that's pretty simple. So how would we apply this? We need a problem first, so it's no fun to talk about things in the absence of some sort of problem to solve. And so I picked a very contrived example. I apologize for this, but I needed an example, so I thought about coloring books. And that seems kind of silly, but there is a good use case for this. I have a child. He sometimes gets bored. He might color on things. I'd rather he was coloring on an iPad that had a ton of options for different things that he could color and fill out with his finger. And so basically, that's my contrived problem we're going to solve. So this is a page from a coloring book, pretty simple, a llama. And if we look at how big it is, it's really not that big in terms of its size, but we're imagining a situation where we want tons of these on a device. So let's look at what it looks like in different formats, right? Bitmap's obviously the biggest. We have JPEG, PNG, GIF, ZIP. GIF and ZIP kind of win there, and then a bitmap is by far the worst. So this is what it would look like. So the question is, knowing something about this data, knowing that it's coloring book pages, can I beat what's already out there, what our existing options are? And we're going to give it a try. So we have to ask ourselves, what do we know about this image that maybe a general compression algorithm or a general data format wouldn't be able to conclude? And the first and obvious thing, which I hope you all realized, is it's monochromatic. There's only 2 colors in this picture. And so generally, when we're talking about image formats, we do try to represent the full color palette, right? And we take an amount of space to do that. But if we know we only have 2 colors, then, being software engineers, we understand that we really only need 1 bit. 0 maybe for white, 1 for black. It doesn't really matter, but we only really need one piece of storage. So immediately, I can already get a 24:1 compression ratio. I can take away 24 bits of space and remove it down to 1. So that's pretty good. That puts us about here, though. We still haven't really beaten GIF as our option, so we want to do better than that. So what else do we know about coloring books? Well, the other thing we know about it is for them to be interesting for children to work with them is that they have to have big blocks of white space, right? Something to color in. And big white space, to me, screams redundancy. We have a lot of information in this image that's really not valuable. It's just the same thing repeated over and over again. And generally speaking, that's a lot of what you think of the basic idea of what compression algorithms do, is they try to remove that redundancy and replace it with some sort of pattern or some sort of token or character that can represent it all. Because ultimately, redundancy is wasted space. We have too much going on. So how can we describe a large block of 2-dimensional space more efficiently is the next question. And the good news is my background gives me a pretty obvious tool for that, and that is a Quadtree. Now, those of you that have never worked with a Quadtree, it's a pretty simple data structure. It looks like a binary tree, but instead of working on a 1-dimensional thing like an array or a list, it works on a 2-dimensional space, takes your space, and it cuts it into quads, hence the name. But think of it as you have a square, and then you cut it into 4 smaller squares. And then you continue this process to the point that you get down to the point that a single square represents a pixel in your image. And then what you can do is you can walk through this structure, and you can look at each square and ask yourself, is it uniform in color within this square? And if the answer is yes, then you don't need that square's children, so you can remove them. And over time, through this process, you can actually remove the amount of storage you require to describe that image. So let's see what this looks like. We start out with our basic picture. We cut it into 4 pieces. We continue to cut it in 4 pieces. Whenever we find a section that is all one color, we go ahead and say, okay, this is a leaf node in our data structure now. And we just continue that process. And I've only highlighted 1 quadrant, because otherwise it'd be very messy if I was showing this. But we would continue on all the quadrants. And eventually we would get to the point where we would have the whole picture represented in this data structure. Now, of course, this is just a data structure. We need a way to actually represent that data structure in a binary file format so we can use it for storage. And that's pretty simple, too. You basically take 1 bit and say, if you encounter a 1, then that means you've read a node that is split, and so you need to look at its children. If you encounter a 0, that means that the node is not split and it's uniform in color. So if something is not split, the next bit is its color, which we already said was only 1 bit. And if it is split, then the next bit describes the children, and you have the next 4 in a row. And you just recursively repeat this process and kind of describe your entire data structure in a stream of bits on the file. So I did this on that particular picture, and I got it down to 11 kilobytes. So I was able to do really, really well with this. And the reason that worked is for that particular picture, on average, a 35 by 35 square block of pixels was the same color, mostly white, obviously. And so it was easy enough to represent this and steal some space out of it. Now, and that's that big, in case you were curious what it would look like blown up on the screen. Now, this only worked because I made some assumptions about the information that we required of the problems for the problem. And so it wouldn't really work on a real picture of a photorealistic llama. It only works because I was able to make those assumptions. But for fun, there is a website out there, and I'm sure a lot of you will go play with it after this talk, that allows you to drag any image you want into it, and it will show you what that image would look like in a Quadtree representation. And so we'll watch this for a little bit. So that's pretty cool. What would we do this for? Like, I have a contrived problem, so you're probably thinking, I don't understand, I'm not in the business of making coloring book pages. Well, there are a lot of images out there that adhere to these same kind of limitations. And one of them is medical images, which I have up there. Medical images tend to be black and white. They tend to have big blocks of one color or the other. And so if you had a lot of medical images that you needed to store or transmit or do something with, this might be a good approach. And in fact, there's several papers out there that discuss using Quadtrees as a means to store and compress and access data in medical images. But it's not isolated to imaging either. The approach could be applied to anything that kind of fit that model of you have a two-dimensional space and a lot of things are uniform within it. So how did we do this? Well, we did this thing called semantic dependent data compression. And it's this idea that you highly customize a data format or a compression algorithm to your data, your understanding of that data to save space. Now, it does require that you also have a problem that you're trying to solve, because this is not something that can be generalized. It's really about that pairing of, here's my data, and here's the problem space in which I want to use that data, and what do I know about those two things? Well, why would we ever do this over just using a general compression algorithm or existing easy to understand format? Well, in some cases, you have enough inside information that you can actually beat a general lossless algorithm. And that's because what you're doing is kind of lossy. You're actually losing a little bit of information, but you've made the decision that the information you're throwing away is information you don't need. It's not what you need for your problem space. But even better, and a lot of reasons why people really tend to do this, is that you can still support nearly or completely random access with some of your approaches. So a lot of times when you're working with a general compression algorithm, the assumption is that you will basically unzip or unpack the entire thing before you work with any data in it. But you can tailor your own algorithm in such a way that it allows you to take out pieces of it and work with that piece and move on. And the Quadtree is a good example of that because, it gives you that quad-based search that you can do on your data set, and it really helps with, zooming images and other use cases. But let's take a step back and let's look a little bit at a general compression algorithm just as a comparison, just so we kind of have an idea how they're different. So LZW is a really good one. It's the one a lot of people like. It's actually one that's really easy to understand, which is why I picked it. And it's one of those ones that's so simple that makes it really clever. And you look at it and you say, of course, when it's all done. This is what we're going to compress. We're going to compress some text. I like llamas. They're funny creatures. Alpacas are closely related and often raised for their fur. So I hope you learned something about these animals today. So if I had this text and I wanted to use LZW on it, the first thing I would do is I'd actually initialize a code table of all of the characters or tokens in that text. And I would basically give them a unique code for them. Now, chances are, if you're using ASCII, it'd probably already be the same value, but you create this kind of idea for it. Well, actually, it would be the same value. Now, then what you do is once you have that initial single character table initialized, you go through the data and you look for character pairs. And every time you encounter a character pair, you generate a new code for that pair. Now, that code has to be greater than your initial data set. So if your initial data set's 8 bits, then your codes would have to be 9 bits in order to make sure that you had a unique value. And every time you encounter a pair, you basically record in the table what that new code is for that pair, until you eventually hit something you've already seen before. And when you've already seen something before, the great news is you go and you get that code out of that table and you replace those 2 characters with your new code, which is now, in this case, slightly bigger than a single character, but still smaller than 2. And you actually would do this process over and over again. So eventually you would have a table of 2 characters to a code, and then you'd have a table of 4 characters to a code, and you continue that process. Now, the cool thing, the really clever thing about this algorithm, what makes it so simple and so awesome at the same time, is that the code table is not included with the data, because you can actually generate it on the fly as you're reading the compressed file, the same way you generated it the first time. And that's what really makes it so cool and why I like it so much. But the interesting thing about algorithms like this is they don't pass judgment on your data. They have no insider information into what's going on. And so to me, I like to think of general compression algorithms a lot like playing poker with pot odds. You know, everyone has the same understanding of what's going on at the table if they're just willing to do the math in their head. But if you're a really good poker player, then you understand the other players at the table. You understand how they may raise or bluff or fold at different opportunities. And so you have that additional information to kind of cheat the system. That's what we're doing with semantic-dependent data compression. So let's move on to another problem space. Let's look at earthquake data. I found out that there's an area in Peru that whenever there's volcanic activity, they have to evacuate all of the llamas and alpacas from that area, and that's really an interesting problem to me. It's like, how do you efficiently evacuate 28,000 animals that have no idea what's going on? And so I'm imagining that we need to write something to facilitate this because, again, another contrived example, but go with it. So we have a data source. We have USGS is nice enough to publish all of the earthquake data in GeoJSON format. So we can kind of say this is our starting point. Let's pretend we had to do something with this data. And those of you who've never heard of GeoJSON before, it's just JSON for geometric features. It's nothing fancy. So the original file size, I went and got a month's worth of data from this area in Peru, and it was 338 kilobytes of data. Not a big deal, but again, we're just going to walk through this example. And I looked at it in different formats. So I said, OK, let's say if we just generated an old-fashioned flat file format, what would that be? If we did BSON, which you'll notice BSON's actually bigger. Kind of a surprise there. And that just sometimes happens with that data format. Protobuf was pretty decent, 172. LZW was 40. We had Smile, which is that compressed JSON format from Faster XML. That's 240. These are obviously not all the formats. I don't have time for that. So those of you that were interested about maybe I didn't hit your favorite format, you can go get the data from USGS and have fun with it, just like I did. Now, one of the first problems we have with JSON in terms of a format is, although it's better than XML in terms of XML was way too wordy and verbose in terms of a data format, it's still very expensive itself because it leverages attribute value pairs to describe the data. And so this means a lot of strings. And strings tend to be expensive. So in general, anytime you have a self-describing data format, it's going to be a little bit expensive. Makes it highly extensible, which is why we go that route. So I'm not saying it has no value. I'm just saying that if we're concerned about space, that's the trade-off we're making. So the first and obvious thing to do for this data set is just get rid of the labels. Take away the fact that it's self-describing. And this actually was a lot of the data, to the point that when I was done, I had removed about 32% by taking away all the labels. But let's keep going. I mean, that's not fun. That's not good enough. We're going to talk about types. In particular, if you think about what might be present in earthquake data, there's probably a lot of epicenters and magnitudes. Where did this earthquake happen, and how strong or how big was it? So that's probably a good piece of that data. How often do we hear this on the news? Earthquake was a 3.14159265359 on the Richter scale, right? We don't ever hear that level of precision when we're talking about magnitude of earthquakes. And yet a lot of times when we store that data, even file format or in our code, we just tend to kind of default to floats or doubles because that's pretty easy. But we don't want to do that because that's not really what we need. More often we see things like this, 6.1, 7.1, 9.8, if it was a really bad day in Peru. So we look at, OK, it's easy just to go ahead and use a double or a float, but the effective range is way too big for what we really need. We need something a lot smaller. So one of the first things we can do with this data set is figure out, what do we really need? Well, we really only need the tenth place. We really only need values from, -1 to 10. And so we can pretty quickly figure out that we just need 7 bits to store that data. We don't need any more. And we have other data like this. Like latitude and longitude is something that often we end up storing in floats because it makes our lives easier. But that's actually one of the worst ways to store that data because it's the same problem that I just showed with magnitude in that we have this limited range. we had this limited precision that we really need, and so using the full floating point type is kind of silly. Same thing with depth. So a lot of times when you first learn about latitude and longitude, you understand this concept of degrees, minutes, and seconds. And that's not an easy type to have in your code because then you have to go create a special data type for that. But it's a really efficient type for how to store the information because you're not having all this extra space that you're not really using. So if you're curious, 1 second equals 30.72 meters. And if you don't really like, the metric system, that's 100 feet. And if you're not good at either system, just imagine 3 buses. So when we're thinking about the problem we're trying to solve, a question we have to ask ourselves is, do we need better than 3 buses? If an earthquake's happening in Peru, how much notice do they need? How much, precision do they need on that position in order to be able to evacuate those animals? And the answer is probably, most of the time, that we would probably be okay with 3 bus lengths. That would probably be okay. But if not, if we wanted to be on the safe side, we could even just say, okay, it's 1/10 of a second is how we're going to store the data. And so we'll play it safe. And we come away with we only really need 24 bits to actually store a latitude or longitude value pretty easily. And we can do the same thing for depth, the same process. And we can get down with 13 bits. And we're going to do this process over and over again for every numeric type we have in the data set and figure out what is this thing really? What precision do we really need? What's our real range of values? And we come out of it, we can take away 6% of the file size just by getting rid of that excess. Again, not a lot, but we're moving on incrementally over time. The next approach, and probably what's the most useful thing to do, is actually to look for pieces in your data that are actually more relative than absolute. And what I mean by that is there information in your data set that you can use the surrounding data to figure out what its value is instead of actually storing the raw value itself. This is an approach that's often used in image compression, where they look at the surrounding pixels and they infer what the value of a current pixel is based on its surroundings. And it can be used for a lot of different data types where you think that the variation between 2 pieces of data in the same data set is not going to be that great. And we have that in this file because this file has a lot of time. And we're looking inside a limited time range. And so since I asked for a month's worth of data, I know everything is in that month, and I know everything is kind of relative to that month. And so this is the amount of minutes in the longest month, so I don't need to store any value bigger than that, because I can start with my start date, start time, and offset from there. And so I can have 16 bits for time. But I can do even better than that, and then I can look at the positions. Here's a map of the epicenters for different earthquakes in the world. Noticing that you probably notice they look like they follow fault lines, right? That makes sense. From a science standpoint, that makes sense. Because they follow fault lines, they tend to be close together. So we actually have another opportunity for this improvement by using relative data, by looking at, can we group these things in a way that within a block, we can guarantee they're within a certain distance of each other. So we can create blocks of epicenters and then say within this block, every epicenter in this block is within this distance. And I would really like to get it down to 1 byte, that I can basically describe the offset from a starting position for a particular epicenter in 1 byte or less. And I can do that. I can do that pretty easily. And that removed 2% of the file. What's left is strings, strings, and more strings. A lot of the data that we deal with is string-based data, and a lot of it's not really needs to be string-based data when we really think about the essence of the data. And this is something I coach on a lot with a lot of the entry-level engineers and the new engineers I work with, is they come out of school and they want to use strings all the time because it's easy, but a lot of the data we're working with really isn't a string, and string introduces errors and introduces complexity that we don't really need. So some of the data looks like this. There's this thing called types that kind of talk about different data in the file. So it might be that, it's nearby cities, it's the origin, it's phase data, it's tectonic summary. It's just a lot of different weird little things floating around in the data. So I wanted to go look at how this kind of was represented and how frequent these different pieces of data were and how they were used in the data set. And just to kind of visualize that process, I made a tag cloud because that's an easy way to visualize it. And you kind of look at some of this and you say, wow, there's a lot of pieces of data that are very few, very frequent pieces of data. And what's really happening if you look at the data format is that these aren't actually strings. They're optional indicators and bit masks in the data. So They look like strings, but the reality is we're just trying to say whether something is or isn't present in that data set. So we're wasting a lot of space storing the full string value when we're concerned about space itself. So we can go ahead and create a bit mask, and I needed 12 bits to do it. And, take the first one and say it's bit position 0, and if it exists, then that's a 1, and on down using powers of 2. And eventually we can actually remove a good chunk of the data set. And not only did we remove some space, we actually made it less error prone, because it's less likely that we're going to have some weird typo in the data that we're not going to be able to understand. We essentially created an enumeration in the file or a bitmask to represent some of that data, so it works out. Next, we're going to look at sentinel values and codes. So in the same data set, there were 2,319 occurrences of the word null. Let's just replace it with a sentinel value. Easy enough. Very simple. Stupidly simple. Let's just do it. But there were other things. There were things like magnitude type, which is an obvious enumeration. Event type, again. There was an alert level, which is really kind of a scale. How severe is this earthquake alert? And so we could take that, and we can actually just make it a numeric value that allows for comparison as well. And doing all that, removed another 3%. Anybody keeping track? Don't worry about it. So now we're down to a lot of strings that really looked like real strings to me. When I actually analyzed them and looked at what's in there, they really did look like things that deserved to be strings. They could vary a lot. They were like weird textual descriptions of the position of the earthquake. Someone probably just typed it in and sent it in and said, this is kind of where I think I felt it. And so that data, if we really thought it was valuable, we could just get rid of it. We could say we don't need it for our use case. But if we thought it was valuable, then what we should really do with it is just use an existing string compression algorithm, because there's no reason for us to reinvent the wheel when something already works well for a general data set. And so we have choices there. The easiest one, the one probably everyone learned in their computer science curriculum, is the first one, Huffman coding. If we wanted to be able to search it efficiently, like we talked about already, about how sometimes for data we still want to have that ability to have some sort of searchable access, and we thought that there'd be a lot of commonality between the strings, then we might use a trie structure, because a trie structure actually can act as a way of reducing the space consumed by a set of strings. We use something in the LZ family, which I already demonstrated one, that LZW, and then there's a really great string compression approach called predictor compression that I'm not going to go into here. And I picked one. I actually picked LZW because it went along with my illustrations, and I was able to remove another 31% of the file. And so that kind of speaks to, again, how much space is spent on string data in these types of data formats. So I have been keeping count. Basically, in the beginning, we took a lot off by removing the labels. We took a little bit off by messing with the numbers. Some came off with the bitmaps and codes. A lot came off with the string compression. And we're down to 37K. Which is left over. And this is probably mostly essential information. There's still opportunity for improvement in this, but we got to the point where we can efficiently work with the data we wanted to work with, and we had the essential information we need. So it's pretty good. But this is not a general algorithm. We made some huge trade-offs. We're going to have customized code that knows how to read this, knows how to create it. We're going to have to worry about how we ever extend this, if we ever need to add more data to it. We're going to have to, if we hire new people, we have to train them to understand it. They're going to get it wrong the first 30 times they try to work with it. So it is a pretty big mess. And so we only really beat LZW by 3K in that situation. So this is a situation where you might, unlike the coloring book one, you might kind of think a little bit about whether you really need to do this or not. We're going to talk about another situation. I'm going to imagine that all those llamas and alpacas have to get off that volcano by bus, just because that makes it more fun for me. And so we need a schedule. We need to know when the bus is showing up to take them somewhere. So what do we know about schedule data? Well, traditionally when we go to some sort of public transportation site and we get information about the timetables, it looks like this. It's all blown up for us, all exploded out. But when we have conversations with people about public transportation data, we say things like, oh, it runs every 15 minutes from, like 4 a.m. to 6 a.m. And then it's every 10 minutes from 6 a.m. to, 10-something p.m. And then every 20 minutes, between 8 and 8:30 for extra service comes into play. That's how we talk about things. Now, those of you that have a background in compression that's done a little bit of research on it, you may be thinking right now that sounds a little bit like this concept of called Gomarov complexity, where basically you can describe a sequence of data in English and sometimes beat the way that it was described in the actual data itself. And it's actually more formal than that. That's like the really lazy interpretation of what this is. But the formal definition is like the complexity of a piece of data and how much space is really required can be described by the Turing machine you would create in order to generate that data. And so they usually have some example like this where they have a pattern repeating and then they show you that you could actually describe the pattern more efficiently than the data itself. And that's kind of what we're seeing here, is that we have this long string of times, and the reality is that we can actually describe it more efficiently as a pattern or as some sort of rule for generating it than we can as the data itself, and so we should do that. Now, I kind of create like a contrived representation for the slide just to kind of understand it, but really what's happening here is we don't even have strings here again. So getting back to that conversation about how if it's not really a string, let's not use a string. Time isn't really a string, so let's not store it as a string. Let's store it as minutes since midnight, because we don't really need full seconds to understand when the bus is coming. They're usually off by a little bit anyway. So let's just say minutes at midnight. And I don't really need these delimiters I have up there. I just have that to make it easy to read, but we could really have fixed width data, and we could do away with those as well. So it actually could be smaller. But we're not done yet. We still have some information that we need to figure out how to store, like how long it takes the bus to get from one stop to the next one, so you know how long you're on it. And that gets back to the idea of relative. This data is very relative. The time that a bus hits this stop is 4 minutes before it hits the next stop, and then 7 minutes, and then 4 minutes, and then 3 minutes, and 4 minutes. And while we all know the realities of traffic and actually riding a bus is that it doesn't really hold to that, the data we have, though, does. And that's what really matters, is that we're trying to take this data and compress it. So the fact that the data we have holds to these patterns, then we're going to leverage it. And so we can come up with a format that is much better, where we basically kind of create this pattern-generating representation, and then we have our software understand that pattern and be able to generate it. Doing this, I can take essentially 2,000 bytes and bring it down to 161 by having that representation. And again, I've done it in a way that I can easily access any point of data I want efficiently, because it's not all kind of lumped together in one big compression algorithm. Now, some of you are probably thinking right now, like, really? You actually expect me to care about 2K? I mean, that's what we're talking about here. Well, that's just an example again. All of these are contrived examples. But in reality, if we were really building a system that had to run on maybe my Pebble that would let me know about when the bus was coming, we're talking about just one route and one bus line in one city. And then you look at New York, and there's 248 transit lines in New York City alone. And that's lines. That's not the number of times that bus runs. That's just lines. And then there's 255 publicly available Google Transit feeds when I looked this up last. So that data could add up, and if we have a very resource-constrained device. And so getting back to that, we're not talking about this. We're not talking about this machine. We're talking more about these machines, and more the low-end ones, right? Because the high-end ones are getting closer and closer to really nice machines. Now, with that, having done all that and talked about how you can do this and how useful it is, I'm going to tell you right now, don't do it. Don't try this at home. When I did this work, I had some interesting characteristics of the work I was doing that made this actually advantageous. That most of the times for most of our development, if we're doing, obviously any kind of client-server development, any kind of desktop development, these things don't come into play. One of those things is that where I was working actually had this goal of intentional obfuscation of the data. We wanted people not to understand our data, and we wanted to make it hard on people to access that data. So having these really weird, kind of crazy data formats was actually an advantage for us, and most people don't have that situation. And if you do have a situation where you want to hide your data from other people, there's a good chance that what you should really be doing is encryption, right? We're not doing compression as our means to hide data normally. And so if you're doing healthcare data or financial data, obfuscation is not the answer. The other thing that recently has kind of resolved itself, but for the longest time when a lot of the systems I had worked on were being developed, was that a lot of the really great compression algorithms were patented. And so while we may have had this option to use this really great algorithm that already existed and would have done just as well as what we were doing, we didn't really want to pay for it. We didn't want to go through the licensing. And so it was easier to hire someone to go develop this format than to actually go enter a licensing deal on a patent. The other important thing is the system that I was working in was entirely internal. And what I mean by that is that none of the data that we were working with we ever expected to be publicly accessible by other individuals. Now, of course, there's people out there that'll figure out anything, they'll reverse engineer anything, and so, of course, they got into it, even though we tried as hard as we could to make that difficult on them. But the reality was we could own every single piece of software that was going to read that data and every single piece of software that could write that data. And that's an important expectation to have if you're going to take an approach like this, because the minute you start doing something really crazy like what we did, and you want other people to actually be able to interact with that data format, you're going to add some complexity in terms of your interactions with your vendors and your clients and your users that you don't want to deal with. And one of the bad consequences of what we did is we ended up in a situation where all of the software we wrote was tightly coupled to the data format that we had. And so as a result, like anytime we needed to do anything, like change an algorithm or change the way we did search or display data, someone who really understood the nitty-gritty details of that data format had to be involved in the project. And so that's a consequence of doing something like this, is that you end up in this weird situation where you've customized your data to the point that it no longer really fits general use. And so with that, I have some advice. If you are here, if you're working in an environment where space, memory, bandwidth is really no object, like you have all the things in the world you want, massive clusters, great machines, everything great's going on, well, I really would strongly suggest that you use an existing, established, easy-to-read data format like JSON and maybe XML if that floats your boat. Now, I do want to encourage everyone to take a YAGNI approach with data. Those of you who aren't familiar with that term, that's you aren't going to need it. It's a big aspect of extreme programming came out about that, about every time we make a decision, let's not code for the future, let's just think about the future. And I think a lot of times with data, we get a little lazy, and we may apply YAGNI to our code, but then we say, like, oh, we have this data, let me just go ahead and release it into the wild, because it's just as easy to have it go out as it is to keep it in. And then when I'm talking about this, I'm talking about this like data formats or REST APIs or different things we do. We sometimes just kind of open the floodgates on our data. And I think we need to stop doing that. I think we need to think more critically about what data we really need to expose and share with the world and what it really should be looking like. And that's kind of that third point, which is still think critically about your types. Like, how do we really want to represent this piece of data? Is it really a string, or is it really something else? If you are a little worried about space, you're in an environment where you do have some concerns about space, then I actually would encourage you to use one of the established IDL or schema-based formats, and IDL being that interface description language. Protocol buffers or protobuf is a great one. Avro or Thrift all work. I still have those second 2 points. Like, I still want you to think about what data you really want to expose, and I still want you to think about your types and what they really are. If you're a lot worried about space, you're developing in a platform that is a little limited on space, then, start with that idea of, like, what do I really need to share with the world? What are those types I really need? And then, if you can, just go ahead and use a general compression algorithm. Don't reinvent the wheel. Don't build your own thing. Just kind of understand that. And if and only if you are completely neurotic about space, and you're and all those things that I talked about having that internal environment and being okay with that tight coupling between your algorithms and your data structures, then think about what we showed here. But the most important thing that I really have to stress is that in addition to building up this format, you really have to plan and test for extensibility of your data. And this comes from the fact that I spent 5 years doing what I call bit twiddling. I don't really call what I did really compression, because I really felt like we just kind of went in and we played with bits and we figured out what the bits should be and did a lot of fun stuff to figure that out. And when I was doing this bit twiddling in my job, the number of times that I felt like we were painted into a corner because someone thought that they had written the data format in such a way that we could add more data to it or we could add another value to our enumeration. And when the reality came and we tried to actually do that thing, it didn't work. It failed miserably. That happened so frequently. It was like the bulk of my job was figuring out how to work around those limitations. And then the other thing to think about is if you're going to take this approach, you're going to expect to have to do a lot of analysis on your data. I remember one project I was doing, I had to prove the number of primes in between a range, and actually did like a mathematical proof to show my boss that we could structure the data the way we needed to based on the number of primes. The good news is all of this work I had to do has brought me a deep appreciation for the nature of data. And I carry that through into other work I do. So even when I'm working with JSON or some other data format, I do think about, like, okay, what does this data really mean? How is it distributed? What does it look like? What are the real range of values? And I've actually created this really great appreciation for thinking about data just like I think about public APIs or public functions or public classes, in the sense of I don't want to let my data out there in the world unless I know I need to. And I've also really got this greater appreciation for the idea that you test for extensibility, that you actually follow through and extend the code you wrote or extend the data format that you wrote and see how it all plays out. And so with that, I had to end with an alpaca. So this is me taking a selfie with an alpaca. And then there's my Twitter handle and, of course, tweet about the conference. We're out of time, so what I'd like to do is that if anyone has any questions, I'll be hanging around here and outside, and you can come talk to me about it. But after that, thank you guys very much.